Hello mathematicians. We're going to have a look now at applications of differentiation of the trig functions. And you'll notice that there are no notes written here, and that's because, as in the case of the logs and the exponentials, there is nothing extra to tell you about applications of differentiation. All the usual stuff about differentiation leading to the slope of the curve at a point, therefore letting you find the slope of a tangent, therefore letting you find turning points, points of inflection, and ultimately sketching the curve applies just here. It's just that we have different functions to differentiate. So this first question here is reasonable. I would say it's about the standard that you might face on a harder advanced paper. So harder advanced question, sorry. So let's have a look at that. So first step was to find the equation of the tangent and normal to this at the point where x equals pi on 4. So step number 1 is to differentiate it, which is by our function of a function rule, remembering that sine squared x is sine of x all squared. Then that will be 2 times sine of x times the differential of sine, which is cos. And if you wish, you can write it like that, which probably makes life easier. And then the second differential, sorry, we don't need a second differential here. So this is the slope of the curve anywhere, and we want the slope where x equals pi on 4. So when x equals pi on 4, that's sine of pi on 2, 2x, and that's 1. So the equation of the tangent is y minus y1. Now we found that y1 by substituting pi on 4 into here, and sine of pi on 4 is 1 on root 2. We square that, we get a half. So y minus y1 equals m outside of x minus x1. We could rearrange this if we wanted to, or if we were given a target, but we'll just leave it like this because we want points of intersection of the axes. Now for the normal, it's y minus y1 equals minus 1 over the reciprocal of that, so minus 1 times x minus pi on 4. And then in part B, we need to do a sketch. So we may not really know that the graph of sine squared looks like this. So it's a sine graph, and where it went below the axis, it's going to come above. It'll have a slightly different shape, but we needn't worry about that. But it will be positive. That's the main thing. And then at pi on 4, sketch in our tangent and normal, and we want the point where the tangent meets the x-axis and the normal meets the y-axis. So we find those by, for point P, set y equals 0, solve that, and we get that expression for x. At point Q, set x equal to 0, do our substitution, and we get this for y. And then we wanted the area of the triangle OPQ. So that's that triangle there, which is a right angle triangle coming from the origin. So the distance OQ is just that. The distance OP is just that. So we just want the area to be half the base times the height. This part here is the difference of squares. And if we wanted to, we could take out another 4, make it 1/8 out the front, outside of pi squared on 2 minus 1, maybe put it all over 2, but again, depends what the question says as to whether you'd be bothered doing that. So I think that's a fair standard of question, solid standard of question for advanced. Now our next question, I put it in here just to alert you to what this textbook can do. You probably don't need any alerting. I think it's pretty good up until sketching the curve, because to sketch this curve, it's really, I would say it's extension 2 standard, at least. It's a difficult extension 2 question to sketch that curve. But as far as the stationary points, points of inflection go, it's just applying a rule. So if we run through that, Part A, find the first and second derivatives of e to the minus x cos x. So we've got a product, that times that. So put down the first, differentiate the second, put down the second, differentiate the first. Take our e to the minus x out as minus e to the minus x out as a common factor, because we've got 2 minus e to the minus x's, and that's what we've got left. Differentiate that again, and we've got once more a product. So put down the first, multiply it by the differential of the second, which becomes that. Then put down the second, multiply it by the differential of the first, which becomes plus e, that should say, to the minus x. So take e to the minus x out as a common factor, and we'll have sine x plus cos x, this one and this one, minus cos x plus sine x. And you can see the cos x's go, so again, lost that minus, 2e to the minus x times sine x. So there's our first and second differentials. To find the stationary points, we know that that happens when y dashed equals 0. So this term can never equal 0. So it's when sine x plus cos x is 0. And that's a fairly difficult problem on its own. That certainly bumps this into extension 1 realms. So we have a feeling that it will happen at 45 degrees, something to do with pi on 4, because that's where sine x and cos x take the same value. But to get exactly where sine x equals minus cos x, we really need to look at the curves. So I've sketched the curves on GeoGebra because my drawing would be atrocious. So this is what the curves look like. So we can see sine x here, that should go on to there. So there's sine x, the orangey one is minus cos x, where I think I've just done all of this wrong. No, small moment of panic, because I can backtrack my work. I do want where sine x equals minus cos x, so it's where the two curves intersect, which is there and there, which will be at minus pi on 4 and at 3 pi on 4, so our 45 degrees. Now, that then means that when I look at the second differential at minus pi on 4, if I put that up into here, this is always going to be positive. So I want sine of minus pi on 4. We can see from our graph of sine here that that will be a negative. So I'll get a maximum turning point there. And at the second differential at x equals 3 pi on 4, again, this is positive. Sine of 3 pi on 4 is positive. So the second differential is positive, so I'll have a minimum turning point. Now, over the page, get the points of inflection. They will happen when the second differential equals 0. So that's when this equals 0. And since this can't be 0, it's whenever sine of x equals 0 over the domain, which is 0 and plus or minus pi. Now, up to there, I think apart from sine x cos x has been reasonable. But to do the sketch, it becomes really difficult because we're dealing with horrible numbers. So we would go through our normal flowchart. Again, I've drawn it here with GeoGebra because mine would be indecipherable. But what clues have we got? Well, as per usual, we can say, well, where does this graph cut the y-axis? It cuts the y-axis whenever x equals 0. So this will become 1, and cos of 0 is 1, so at y equals 1, so that's that point. Where do we cut the x-axis? Well, that will be where y equals 0. So where does y equal 0? Well, this can't be 0. So where does cos x equal 0 over our domain? So if we think of our cos curve over this domain, it's going to go down like that, and like that. So that's at pi on 2 and minus pi on 2. So that's this point and this point, so that's all good. Our turning points were at pi on 4, this point, and 3 pi on 4, so this point. This one was a maximum, this one was a minimum. We would get those values by putting back into our original equation, which is horrible enough. And then what happens after that is that we've got our point of inflection at 0. So when x equals 0, this curve switches from being concave down here to concave up here. And we've said plus and minus pi as well. Now, if we extended it beyond this, what we actually see is that the inflection does change here. I can't draw it onto here, it's all too small. But it changes here, and it runs like this towards the x-axis. And this one here goes down a long way until at minus pi, it actually changes concavity. And what we see over here is like a huge version of this, because this models damped oscillations. It's worth punching it into GeoGebra and just zooming out and seeing if you can get a feel for this graph. But you can see why they zeroed in on this particular part of the graph just here. So, extreme, too extreme, definitely not an extension 1 question for that part. Other bits are okay, but the bit where sin x equals minus cos x is again really stretching it, even for an extension 1 question. So, have a go at these ones out of 14H. As I always say, you should think about what the big idea is, but the big idea is the same as it always has been. Maybe it's worth jotting that down again though, because I know that it's not automatic for everyone at the moment. It should be. What's the significance of the differential?